1 trillion watts of AI power built in space. This isn't science fiction, it's TERAFAB. In the last 24 hours, this announcement has taken over tech, AI, and finance conversations worldwide, and it could change everything. Let's break it down.
Welcome. Today we are looking at bypassing terrestrial limits, a 2026 engineering roadmap that outlines how SpaceX, Tesla, and xAI are converging into a unified ecosystem. We will examine the core bottlenecks in launch cadence, silicon fabrication, and autonomous dexterity, and explore the radical engineering pivots we are making to overcome them. Progress today is not halted by a lack of ideas, but by strict physical and economic limits. Earth's constraint boundaries in energy, compute, and labor are threatening to stall the AI singularity. Our strategy is to operate SpaceX, Tesla, and xAI as a singular mechanism engineered to break these terrestrial limits, what we call the orbital solution. The first major bottleneck is energy. Terrestrial power grids simply cannot support the energy density required for true AGI. For every 300 megawatts of raw compute, operators must generate a full gigawatt to account for infrastructure, intense cooling demands, and maintenance margins. To reach the 1 terawatt required for true AGI, we would need twice the total energy output of the entire United States. We cannot rely on the terrestrial grid when gas turbine manufacturers are already backlogged through 2030. This drives our first major pivot, moving to orbit. Space offers an environment with 5 times the baseline solar efficiency of Earth, with 100% continuous solar exposure and zero need for massive battery infrastructure. Furthermore, cooling in the vacuum of space is vastly more efficient. Our strategic target is to make space the most economically compelling location for AI within 36 months, by launching 100 gigawatts of solar power and AI silicon into orbit every year. But moving data centers to space introduces our next hurdle, the mass-to-orbit bottleneck. Launching 100 gigawatts of orbital compute requires moving 1 million tons, or roughly 100 million AI chips every year. That demands about 10,000 Starship launches annually, roughly 1 launch every single hour. The Falcon 9 is only partially reusable and cannot meet this demand. We need a fully reusable vehicle. This brings us to our materials pivot. To achieve this unprecedented launch cadence, Starship had to abandon carbon fiber in favor of 300 series stainless steel. Carbon fiber is nearly 50 times more expensive, requires massive custom autoclaves, and shatters under extreme cryogenic stress. Stainless steel, by contrast, is highly cost-effective, easily welded outdoors, and natively handles cryogenic temperatures, while possessing double the melting point of aluminum for atmospheric reentry. Even if we solve the launch bottleneck, we are heading toward a massive silicon deficit by 2029. Current leading foundries like TSMC are fully saturated. Because it takes at least 5 years to bring a traditional fab online to volume production, external supply chains physically cannot scale to produce the 100 million chips we need to fill Starship's payload capacity. Our solution is Project TeraFab. We are internalizing a massive 2-nanometer foundry designed to produce 1 terawatt of computing capacity, or 100 to 200 billion chips per year. This vertically integrated process will produce our next-generation Tesla AI5 and AI6 chips, with 80% of the output earmarked directly for our orbital solar data centers. We must, however, confront harsh industry realities. While we successfully vertically integrated battery cell production to cut costs in the past, semiconductor fabrication is an entirely different beast. Tesla currently possesses zero semiconductor manufacturing experience. 2-nanometer fabrication requires pristine ISO Class 1 to 3 clean rooms, where even a human breath destroys yields. A challenge so steep that NVIDIA's CEO has warned matching TSMC is virtually impossible. Back on Earth, our terrestrial operations face a crushing labor bottleneck. Driven by a sub 1.0 replacement birth rate in the U.S., Pure demographic and industrial math dictates an overwhelming manufacturing defeat against China's massive labor pool and electrical output. Our only countermeasure to this demographic destiny is large-scale automated manufacturing and a robotic workforce. To bypass these legacy manufacturing bottlenecks, we are introducing the unboxed parallel assembly method for the Cybercab. By ditching the traditional linear assembly line and building the vehicle modularly in parallel, we can achieve a production rate of one vehicle every 10 seconds. This allows us to hit a $25,000 unit cost, with initial production ramping up in April 2026. To solve the broader labor shortage, we are deploying Optimus. Optimus learns through a continuous sim-to-real data engine, where millions of digital twins in a physics-accurate simulator exchange edge case data with over 10,000 real robots in the physical world. The ultimate trajectory here is recursive manufacturing. Optimus robots building more Optimus robots to generate exponential industrial output. Deploying these AI-driven physical systems renders traditional validation paradigms obsolete. The legacy V model relies on highly predictable hardware and physical prototypes. But AI is non-deterministic and evolves constantly via over-the-air updates. The sheer volume of edge cases makes comprehensively physical testing an economic and mathematical impossibility. Instead, we are adopting a flattened V model centered on continuous integration, testing, and deployment. We route raw sensor data directly into end-to-end neural networks and decouple validation from hardware availability. Using massive-scale parallel compute and high-fidelity virtual proving grounds like Omniverse, we shift the entirety of our testing to a rapid iteration digital twin environment. When you zoom out, you realize this is not a portfolio of separate companies. It is the cosmic flywheel, a single, closed-loop machine engineered to break Earth's physical constraints. XAI software orchestrates the logic. Optimus scales the physical construction of our TERAFAB foundries. TERAFAB produces millions of AI chips. SpaceX launches that hardware into orbit. And those orbital data centers harvest infinite energy to train the next generation of XAI and Optimus.
So the real question is this the future of AI infrastructure, or is it too ambitious to work? Let me know what you think in the comments. And follow Maya Ellis for more deep dives into the future of tech.